Hello and welcome to day 19 of our STL Mastery series. Today we are diving into an advanced but essential concept in C++ STL, custom comparators in sets and maps. This lesson will unlock a powerful layer of control over your containers and elevate your understanding of how data can be stored, accessed, and sorted efficiently and intuitively. So let's begin. Here's what you will take away from today's session. First, you will understand why default sorting isn't always enough and when custom comparators become necessary. Next, you will learn how to implement custom comparators using three primary approaches: functors, lambda functions, and operator overloading. And finally, we will see how these techniques are used in real-world applications like ranked lists, task schedulers, and leaderboards. By default, ordered containers like set and map use std::less, which sorts elements in ascending order. But what if you want descending order, or need to sort a complex object like a student by marks and then name, or organize employees by salary? These cases can't be handled with default behavior. That's when you define a custom comparator, giving you precise control over how elements are compared and stored. This is especially important in real-time systems, dashboards, and algorithm challenges. Let's start simple. The greater comparator is built into the STL and reverses the default sort order. In this example, we use set int greater int and the numbers are stored in descending order from largest to smallest. It's a handy shortcut when all you need is reverse sorting and you don't want to write custom code. Now let's go deeper. A functor is a class or struct that overloads the function called operator. In this example, the test functor compares two integers and returns true if the first is greater than the second, achieving descending order. Functors give you flexibility. You can keep internal state, reuse the logic, and even template them for multiple types. Functors are especially useful when dealing with user-defined types. Take this student struct. It contains an ID and a name. The default comparison won't know what to do with it. By creating a compare by ID functor, we define custom logic to sort students in their ID. Without this, the set would not know how to insert or arrange the students at all. Sometimes you don't need a full functor. You just need a quick comparison for a one-time use. Lambdas are perfect for this. Here we define a lambda that compares two pairs by their second value. Using take type and passing the lambda into a set, we achieve custom ordering inline. It's elegant, functional, and keeps code concise, especially for sorting collections of pairs or tuples. There are a few things to keep in mind when writing custom comparators. First, your comparison must follow strict weak ordering. This means it must be consistent and logical. Otherwise, the container's behavior becomes undefined. Second, remember that in maps only the keys are compared, not the values. Also, unordered containers like unordered map or unordered set don't use comparators, they rely on hash functions. Lastly, if your object already overloads, you may not even need a custom of comparator. Here's a realistic and very common use case: sorting students first by their marks in descending order, and if the marks are equal, then alphabetically by their names. To achieve this, we define a student struct and a comparator that first checks marks and only checks names if marks are tied. This compound logic is a classic pattern, and you will encounter it frequently in ranking systems, data dashboards, and competitive programming problems. Now let's put your knowledge to the test with a few mini tasks. Try creating a set that stores integers in descending order. Then define a map that uses a custom object as the key, stored by a specific property like name. Next, write a lambda comparator to sort a set of pairs. And finally, write a compound comparator that sorts based on two fields, like we saw in the last slide. These mini challenges will help reinforce your understanding. Custom comparators often show up in interviews. One common question is, how do you sort a map by value instead of key? This isn't directly supported, so you would extract the contents and sort them manually. Another question, how do you sort a set of structs? Here you would use custom comparator, just like we did with students. Finally, many candidates get tripped by unordered containers. Remember, they don't support custom comparators because they use hashing instead. To stretch your skills, here are some practice problems. Build a system that stores employees sorted by salary with a fallback sort on each, or create a live leaderboard where participants are ranked by scores and names. You could also design a data structure that automatically maintains the top n items using a custom rule. Each of these problems will challenge your comparator logic and sharpen your STL fluency. Here's a quick summary of what we have covered today. We explored the built-in filter comparator. We wrote functor-based comparators to sort integers and structs. We used lambda expressions to simplify custom logic inline. We handled stack comparisons and applied these concepts in real-world scenarios. Each of these tools gives us tighter control over our data structure. Before we wrap up, here's your homework for today. First, design a leaderboard using set or map, sorted by score in descending order and name in case of ties. Second, create a task manager where tasks are sorted by priority from high to low and for equal priority by earliest deadline. These tasks mimic real world problems and will solidify your mastery of custom comparators.